All right, hello everyone. Welcome back to Historical Geology 1404. Some of you may have noticed that I brought some guest speakers to join us today. My two youngest children, Liam is 3 and Isla is 4. You're 4, right, Isla? Yeah, you're almost 5. They're at the back because I skipped class on Monday because my wife was summoned to jury duty. She was in the jury all day on Monday. She was in the jury all day yesterday. And the trial is still going, so she's going to be in jury all day today. And so I still have my kids, but I cannot miss another class with you guys, so they are joining me. So just bear with us, as occasionally they may call for my attention. I may, out of the corner of my eye, see my 3-year-old eating Play-Doh and need to run over there real quick. Just whatever it is, let's just roll with it today. Today we are going to be having the last lecture. We're going to be covering just the last little bit of Earth history here, mostly concerning the development of our species and our civilization. And then we're going to move into our final exam review, which will open today. Your final exam will open today and close tomorrow at midnight. So assuming that we end on time, your final exam will open around noon and close at midnight tomorrow, meaning you'll have about 36 hours to take both exams. Okay? I wish that wasn't the case, but as I've explained before, that's just the way that the math worked out this semester, because for some reason they had the semester start on a Tuesday instead of a Monday, and we are a Monday, Wednesday class. Yes? Yes, my love? Liam has an ouchie? Liam, are you okay? Yeah? Good. Yeah. All right. So some things that happened over the last week. There was an earthquake just across the border in New Mexico. Some of you may have felt that this weekend. It happened on Saturday night. I felt it just a little bit. I was having a movie night with my friends. It was kind of funny, actually. You guys ever seen A Quiet Place? Okay, we were watching A Quiet Place Part 2 with my friends. They had never seen it. And so it was a really quiet part of the movie. And then we felt like there was a little clink of glass like in our house, and everyone just kind of like jumped, like, what's in the house? And then I looked at my phone, I was like, oh, there was an earthquake just over in New Mexico. It was the perfect timing. Good morning. Some of my children are joining us today. Okay, and then a development that I actually did not know about until earlier this morning, when it was pointed out to me. India and Pakistan seem to be lobbing missiles at each other as of this morning. Yesterday, things were pretty tight between them, and now, as of this morning, they're actually shooting at each other. So, two extremely powerful military forces here. Pakistan backed by Russia, India backed ironically by both China and America at different points in time, although more China right now. Hey, Liam, I need you to share that with your sister, okay? Please? All right. So we'll see how that develops throughout the course of the day and for however long it lasts. Hopefully it doesn't last long, because that would be a very, very bad thing if those two countries actually went to full-on war with each other. Okay. Any questions or comments, anything else you want to bring up, anything else you want to talk about before we get started today? Yes?
I heard there's an old Soviet probe that's about to crash land back onto Earth.
An old Soviet probe that's about to crash land back onto Earth?
Because I think it was supposed to go to Venus.
Huh.
But it was a design fail, and so it couldn't escape our atmosphere.
Right. Okay. So I haven't heard about this particular story about a Soviet probe that was supposed to go to Venus but couldn't through a design flaw and got stuck in our orbit. That sounds very likely. There were more failed launches than successful ones for about 20 years at the beginning of the space race there. We only talk about the successful ones because they're the ones that made it into the history books more than anything. But then our orbit is littered with all of this debris that people just didn't pay enough attention to back then. And even the smallest little bolt, like that tiny little screw that you're so annoyed that you can't find when you're trying to put your bed together, and like your IKEA bed or your bookcase, right? And you're like, where's that screw? Where did it go? You can't find it, and you never find it. something that's small in our orbit, speeding up through its gravitational orbit of our planet, it goes to thousands of miles an hour, can blast right through the wall of a space station or right through the wall of a space shuttle and kill people. So debris like that is something that we very carefully track. Anytime a new piece of debris is found, we track it, we figure out where its orbit is. Yes, Isla? What is it? He can open that. It's more Play-Doh. Okay. Yeah, they need to track all this stuff so that any new infrastructure we put up there doesn't get destroyed by a random screw. Or even, ironically, human waste. You know what human poop turns into when you jettison it into space?
Frozen.
A bullet. Right? It just becomes a bullet. Instantly flash frozen with enough mass and speed, that thing can destroy a space shuttle. So we have to carefully track all of that stuff. There's actually an international effort right now, which I strongly support, to go up there and specifically collect all of that debris from orbit. It would take a lot of money to track it all down and collect it, but basically clean up the neighborhood above us, so to speak, so that there's actually more real estate to spread out and put more satellites and more space stations and stuff around. Because right now, most of Earth's orbit has too much debris to use, which is why it's all confined to very particular orbits further and further from our planet. And a lot of that debris does come raining down. If that chunk of poo does come through our atmosphere, it'll burn up and disintegrate before it ever reaches the surface. But as long as it's up there, it's a threat to anyone that's flying around up there. So there are people who are trying to push to get all of that space cleaned up, right? Yeah, interesting story though. Thank you for sharing. Anything else? Okay. I did upload last semester's footage of Lecture 12 for the Mesozoic. I hope you all got to watch that, listen to that. Yeah? If not, today might make a little less sense. As you are well familiar with, all of these lectures build on each other. Okay? So having watched Lecture 12, Lecture 13 will make more sense. But I will proceed with our lecture as if you have watched it. And if you have not, go back and take care of that as soon as you can. Okay, so we're starting with the Paleogene today. What was the big thing that happened at the end of the Mesozoic? Yeah, a major extinction. A big one, but not the biggest. Remember, the end Permian one is the biggest one that we know about. But the Cretaceous extinction was still very respectable, okay? A very large extinction. Namely, what was the dominant group of organisms that it wiped out? Yeah, the dinosaurs, exactly. The dinosaurs, the flying reptiles and the swimming reptiles. Now, for those of you that did not watch the lecture, this might make a little less sense when I say those. There never were at any point in time flying or swimming dinosaurs, at least not until the birds showed up, right? Those animals that were swimming around in the oceans and the ones that were flying in the air, like the pterosaurs, were not actually dinosaurs. They were a different group of reptiles. So we just kind of call them flying reptiles and swimming reptiles to differentiate them from dinosaurs. Dinosaurs had a few distinct characteristics, one of which was certain hip structures like this. I talk about this in that lecture, okay? Your Saurischian and your Ornithian dinosaurs were separated by their hip structures, okay? But that's not what we're talking about today. I just wanted to reference that. Okay, so the dinosaurs went extinct. What filled those niches? Because remember, a niche is basically an apartment in that building, that giant apartment building that is an ecosystem, where every apartment is a niche, a space, a function that is filled within that ecosystem by an organism. Photosynthesizers, consumers, dominant predators in the ocean, dominant predators on land. Each one of these niches is filled by one or more organisms in that apartment, so to speak. So now that the dinosaurs are gone, and the dinosaurs, by the way, filled a lot of these niches. When I say that they were dominant, I mean it. For hundreds of millions of years, dinosaurs filled a lot of these niches, okay? Which is why there are fossils of them all over the planet. So what filled these niches? Well, a few things tried, okay? Mammals started to get larger. During the Mesozoic, mammals were small, rat-sized, lived underground or in trees, came out at night most of the time. And why was this advantageous? Because it kept them away from the dinosaurs that tried to eat them. So that's how mammals lived for a long, long time. Well, now that the dinosaurs are gone, their biggest threat, mammals come out and they can start getting big again. Okay, so mammals start to grow. Mollusks. There's a change here, a change in the dynamic between the mollusks that we see in the oceans. I'll talk more about that in a minute. Teleost fish, which represent the many-finned kind of ray-finned fish that we have around today. All of the modern bivalves that we have, our clams, our oysters, mussels, so on and so forth, scallops, start to come back real strong here. Where before, by the way, the bivalves were kind of took a backseat to the brachiopods. Now we have seen that transition where the bivalves now are more dominant than the brachiopods. And then scleractinian corals. Scleractinian corals form the group, the core of all of these reef systems now, because you remember we've lost all of those rugose corals and the tabulate corals. And then we lost our hexacorals that became dominant in the Jurassic, okay? So now scleractinian corals, our modern group of corals, are what form the basis of all of these reef systems. Good job, kiddo. Yeah, that's a wonderful castle. Okay, so the Paleogene, this right here, 66 million years to 23 million years, includes the Paleocene, the Eocene, and the Oligocene. So, there during the Paleocene, right there at the beginning of the Paleogene, I know, confusing, Paleocene, part of the Paleogene, okay? We see mammals getting larger, and we see all the different groups of organisms that we would observe today, interacting with each other today, in an ecosystem together, today. If I were to go out to the African Serengeti and observe the ecosystem there, and then go and observe the same ecosystem back during the Paleogene, I would see a lot of parallels, okay? We see the development of the beginning steps of what we see today starting here, okay? So, what happens after an extinction? What's the key word? That's the thing that we learned how always happens after an extinction, after a bunch of things die. The surviving things do what? They go through a radiation. Remember, there were two terms of that word radiation. One is highly energized particles that are blasting out from a source. And then the other one is an expansion in the diversity available in an ecosystem, or the diversity that occurs in an ecosystem, okay? So the surviving organisms go through this radiation. They diversify quickly. They fill all these different niches. Where before one mammal, maybe a tiny little rat-like mammal, filled a niche where it was a nocturnal, insect-eating, arboreal predator, okay? So lived in the trees, right? Are you throwing that away? Okay. Now that the dinosaurs are gone, there's more niches available. Those little rat-like creatures start expanding into different niches. And so we've got maybe something that looks like a beaver and chops down trees. And then over here we've got something that has taken to the water and kind of starts looking like a whale. Okay? Not that long. Yeah, sure. Thank you. Okay. The foraminiferans, which remember are those little microorganism animals. Did it not work? Oh. Hello.
Hi.
The foraminiferans, which remember are those tiny little plankton, microscopic animal creatures. During the Cretaceous and the Jurassic, there were so many of those things that if you drank some seawater, it would have basically had the nutritional value of soup. Like, taking a spoonful of seawater during the Cretaceous and then looking at it through a microscope, you would have seen it crawling with all these little microscopic little bugs, okay, living in the oceans. The Cretaceous extinction wiped out all but 3 species of forams. Only 3 species survived. They got that close to completely dying off. Well, from those 3 species, they exploded again in the oceans because there was all that living space, rapidly diversified, went through that same radiation, and now the seas in the Paleogene became filled. Liam. Yes, my love? I'll open it. Bring it here. For anyone wondering and who wasn't here when I made the first announcement, my wife is still in jury duty, and so my children are joining us today. Okay. Where was I? Right, and so we get this massive diversification of foraminiferans in the ocean until today. Here we are again with hundreds of different species. But they all came from these three that survived the Cretaceous extinction. Reefs took a while to come back for not because of the fact that there weren't enough corals around, but for a slightly different reason. How many of you are familiar with the microbiota that you have in your stomach? I've mentioned it before, but I'll just recap. In all of your stomachs, everyone, with no exceptions, there is a colony of bacteria and archaeans that lives in your stomach and processes your food for you. Okay? Your body's not doing it on its own. You have a symbiotic relationship with a microbiota colony of organisms in your stomach. It is those things that process the food that you eat. It is those things that develop the byproducts of things like gas. If you're gassy, if you fart, it's I know, not a good thing to say in most society, right? Not something to reference. Yes, my love. You need to go potty? Okay. Hold, please. You know what? Here, I think I can pause. Can I pause the recording?
Yeah.
Let's see if it'll let me pause it. Aha! Right, so, farts. I've said that 3 times now. Professor Hart, please stop saying that. Sure, I'll stop saying it. What makes them, though? Okay, it is the process of that bacterial colony in your stomach breaking down the food and making gases as a byproduct. A common one being methane. Most of what that expulsion of gases is methane, okay, and a few other things, okay? But that's the process of this microbiota in your stomach breaking it down. Isla, I'm teaching. I need you to take care of it, please. Thank you. Okay, so why did I bring this up? Because coral have a similar symbiotic relationship, okay? So the corals, the animals themselves, would catch food, and then at some point, they made a symbiotic relationship with bacteria that were specialized to break that food down. So the bacteria performed the function of digestion, and the coral benefited from getting the nutrition from that digestion, and they contributed by catching the food themselves. What? Isla's not sharing. Isla, please share. Thank you. So, the problem was not that the corals seemed to be too harmed by this, but that the bacteria that they had this symbiotic relationship with seemed to have gotten hit hard by this extinction. And so if that symbiotic bacteria got wiped out, then the corals themselves had a hard time regrowing. Okay, so reefs stayed pretty small and sparse for a while, until it appears that they made a new symbiotic relationship with different bacteria, and then they started to get large, and here they are today, with a few fluctuations between now and then. Okay? Our major marine predators, bless you, believe it or not, the largest marine predators for a long time were not sharks. They were, in fact, whales. Yes, my love? Isla, please share. Declan or Liam, go back. Whales got very big very fast, and they did not look like the whales we had today. Have you guys ever seen a sperm whale? Sperm whale. Have you seen a picture of a sperm whale? The big ones with the boxy heads and the giant teeth. Okay, so think something like that, but much larger and much scarier. Okay? Imagine 60, 70-foot long whales with teeth this big, sort of stuff. Okay, that would eat you. Think of a bigger, meaner orca. Orcas are jerks, by the way, if you've ever wondered. They are mean. They are cruel. They are capable of these things. They're actually highly intelligent. Yes.
I thought they were closer to dolphins than
Orcas? Yeah, orcas and dolphins. Well, those are all whales. They are in the group whales, cetacea. But dolphins and orcas are much closer related to these kinds of predatory whales than they are closer to the ones that we've got like humpback whales, right? Or gray whales. They're much closer, orcas and dolphins are much closer to these kind of predatory whales, okay? They're the descendants of those. So they have real teeth. They have hunting instincts. They will hunt down their prey. And they are highly intelligent. It's very likely, they're still figuring this out, but it's very likely that orcas and dolphins are the next most intelligent species to us. Yes? Liam, please share with Isla. It's like this all day, every day, by the way, in case anyone's wondering. Anyways, so whales, very large super predators, okay? Sharks, though, sharks started to get big too. Sharks and whales were competing with each other. If you've ever heard of Megalodon, right? Yes, that happened. Megalodons were alive during the Paleogene. I have several teeth up here. This one is a replica of a real tooth. That is its actual size. Megalodon tooth. Oh, I'll have to fix that later. Thank you. This is a real Megalodon tooth. I'm not going to make anything. I got to teach, kiddo. You got to make it. Okay? This is a real Megalodon tooth, fossilized. Okay. Have you ever seen The Meg with Jason Statham? Okay, so that's about the size that we're talking about. Okay? The smaller one of those is about as big as the Megalodons were. The larger one is a little bit of an exaggeration, as is the fact that they could live at the bottom of the ocean, but there's lots of problems with that series. Okay, you're going to have to go work it out with her, kiddo. All right. Now, for plants, recall from our discussion of the Mesozoic that now we have flowering plants on the scene. For most of plant history, there were no flowers. We only talked about the development of gymnosperms, right? The cone seeds, right? The seeds in cones, they spread that way. In our last lecture about the Carboniferous and the Permian. All right, Liam, do I need to take away the Play-Doh? Isla, do I need to take away your Play-Doh? Then share, and please take care of Liam so he doesn't yell. Thank you. So now, during the Cretaceous, we see the development of flowers. I had a student once in my class who was so sad that there were not flowers on the planet for so long. She's like, but wait, what did all the dinosaurs give their girlfriends? I was like, that's a very sweet thought, but probably nothing. Yeah, exactly. Something dead? Here's dinner, honey. But yeah, flowering plants didn't show up until the Cretaceous. Neither did grass, by the way. Okay, that's something else we learned about the Mesozoic. Grass will come into big play here in not too long. All right. Okay, so grass has not been around for long, but is now starting to move out and become larger, kind of fill in more field space where ferns used to be. Okay, so they're no longer restricted to the wetter areas. That's a beautiful starfish. Okay, so this is what our mammal development looks like. Okay, so definitely mammals around during the Jurassic. None of them got very big. None of them got very widespread. Most of them, as a matter of fact, died off at the various points. A few survived, though. Our multituberculates became a very successful group, the most successful group of mammals for a long time. But you'll notice that they actually die out here during the Paleogene. This is our Paleogene right here, right? They became very successful right after the dinosaurs. They were doing pretty well for themselves during the dinosaurs, but after the dinosaurs died, they became very successful, and then they started to die off here. Why would that be? We'll talk about that in just a moment. Some other larger groups that you may recognize are whales, diversifying, getting bigger, okay? Rodents, take a look at that. We'll come back to that in a minute. Definitely becoming more successful through time, okay? Carnivores, this includes dogs and cats right there. But also look over here. monotremes and marsupials were alive during the dinosaurs time period. Okay? And they are still alive today, though they are not nearly as common as the placental mammals that we have, the variety of placental mammals. So during the Paleogene, we see all 100 families of mammals that we have today. I mean, there have been a few that have disappeared since the development of human civilization, but for the most part, 100 families of modern mammals developed during the Paleogene and were still around in modern times. Okay? During this time, horses showed up, but they were about the size of house cats. Hard to believe that, but remember what I told you about evolution. Evolution tends to favor increasing body size through time. A successful mutation is often one that makes your body bigger, especially if it comes at an advantage for not being hunted. Well, these things were hunted quite often because they were small and easy to catch. And so becoming larger over time was definitely an advantage to them. We see a differentiation in our hoofed mammals. So hooves developed when toes fused together, and we get even-toed ungulates and odd-toed ungulates. That's how we differentiate them. Okay? So things like camels and bison and pigs have 2 or 4 hooves. Okay? Whereas things like odd-toed ungulates have 1 or 3. Okay? Horses, tapirs, and rhinos. Okay? Yes?
Are bison buffaloes?
Okay, yes. So let me explain the difference there. She asked if bison are buffalo. So here's the deal. The animal that people most commonly refer to as the buffalo here in North America is actually a bison. So we call it a buffalo. That's a European thing. For a long time, there was an animal in Europe called a buffalo that looked a lot like the North American bison, but it was hunted to extinction, I want to say in the 14 or 1500s. They hunted it to extinction for food and for other things, and some of it got domesticated and with modern cows, and that's there's a little bit of their genetics in modern cows, but the species itself was lost hundreds of years ago. But then when Europeans went to North America and they found the bison, they thought, that looks a lot like the buffalo our granddads keep talking about. And so that's where our tradition of calling the North American bison a buffalo came from. But they are actually bison. The buffalo is technically extinct. Right? Except for a variation in Southeast Asia called the water buffalo. Okay, that's a, yeah.
Yeah, you looked up buffalo animal and it says American bison.
Yep, exactly. Yeah, so you look up buffalo and it says American bison. That's most of the time what people are talking about. Yes. But yeah, so those are even-toed ungulates. If you ever look at horse hooves, notice that it's just one hoof. That's one toe. Yes, my love? I'm sorry, you're bored. There's no way around it. You got to play with your toys and your Play-Doh and eat your snacks. I'm sorry. Do you want to stay up here with me?
Yes.
Can you stay quiet? Okay. Rhinos, though, they have 3 toes if you look at their feet. Okay? You can stay up here if you're quiet. Okay. Elephants. So at the beginning of the Paleogene, we see the development of this organism right here, this animal, Moeritherium. Doesn't look much like an elephant. It kind of looks like a pig with an attitude, right? And unfortunately large teeth. Well, it's more or less what it was, okay? And notice also 1, 2, 3, 4, 5 toes there, right? However, by the end of the Paleogene, they have become more along this, Paleomastodon. You can tell that they are from the same, that this came from this, by following the fossil record and tracking the changes in their anatomy. For example, look at this nose, this kind of wiggly tapir-like nose. Okay, as a matter of fact, the tapirs are also descended from common ancestry here. Okay, look at these teeth. Those teeth look vicious. You could probably rip something apart with those teeth, and yet they didn't. That's not what these teeth were for. These were not carnivores. These teeth were intended for digging around through the mud and pulling up roots and tubers and eating those. Okay. Then there's the general body shape, and look at these ears, by the way. Notice that these ears are kind of like rat ears. Very common to the ears that they had from those rat ancestors that lived during the dinosaurs. Now let's go to tens of millions of years later, and here we are, that nose has turned into a short trunk. Look at the teeth. The teeth are the same, except they've gotten larger and bigger, along with a larger body size itself. The ears, you can still see, have the same shape. They've just gotten longer and droopier. And can you see how one day these will become those wide, flappy elephant ears? Paleomastodon. The next step after this are the things like mammoths and mastodons that we see coming up in the next age. Okay? Now let's talk about rodents. This is not a rodent. It looks like it. This is a multituberculate, which, remember, let's go back here. No, too far. Go back here. Here are multituberculates were the most successful group of mammals during the dinosaur time, and then the most successful right after the dinosaurs, but they started to peter off. Well, why? Someone give me a theory. Why would this very successful group of mammals start to become unsuccessful through time, moving into the Paleogene? Well, don't be loud, guys. Okay, so it might have gone extinct through diversification into other species. Not really what happened, but that's a great thought.
Since they were around with dinosaurs, they weren't as good as doing. They were competing for the same thing, and then they died off competing for the same thing because they weren't as good at doing it.
Excellent observation. When they were living around the dinosaurs, they were not competing for the same resources as those dinosaurs. At least not most of the time. But now the dinosaurs are gone and the rest of their mammal cousins are diversifying, guess what? They're competing for the same resources as the other mammals. Okay? But here's the problem. They couldn't adapt as fast. Okay? So notice that as the multituberculates are kind of dying off here, our rodents are picking up speed, as are a bunch of these other ones, primates, creodonts, over here, odd-toed ungulates. But most importantly, I want you to notice the tie-in between the multituberculates and the rodents. As the multituberculates died off, the rodents really started taking off. Okay? Let's go one more. Okay. You need to get past? Hey, I'm standing here. All right, hold on. Liam, turn her the other way. You're going to run into this wire here. Okay? Push her that way now. There you go. This is why. This was a big part of the reason why the multituberculates couldn't compete. Because rodents developed something called continuously growing teeth. How familiar are you all with rats or mice? In particular, rats. Are you familiar with has anyone ever told you that rats can chew through metal or concrete? They can and will if they think there's food back there, behind those things. Why can they do this? Why can they use their teeth to chew through this stuff? Because their teeth are always growing, continuously growing, always and forever growing, renewing themselves. You and I, we grow 2 pairs of teeth. Our baby teeth and then our adult teeth. And if we lose our adult teeth, we're out of luck unless we put something synthetic in there, right? But rat teeth just keep growing, okay? Layer after layer after layer after layer. And so they can chew through a bunch of stuff with it. Multituberculates didn't have that advantage. Once their teeth were gone, that was that. So once a multituberculate has chewed through enough seeds or hardwoods or whatever it is that it's chewing through to eat food, its teeth have worn down to the point where it can no longer eat, that multituberculate dies. But you know what? Rodents can just keep eating and chewing. And this was a major advantage. Actually, this is an advantage. Continuously growing teeth is something that we see other animals develop the adaptation for as well. But in this particular case, this is why the multituberculates went extinct at the end of the Paleogene, is because of rodents and their advantage with their teeth.
If they stop eating, would their teeth keep going and hurt themselves?
Yeah, actually, there are some animals that have that. Wild pigs, wild boars, will grow their tusks. You know, their tusks that kind of curve back on themselves. I've actually seen wild boars where they've lived for long enough and their tusks haven't grown to the point where those tusks curve around and then grow into the face again. And it's gross. This like infected and all nasty around where it's grown back into the face. It's like, yeah, imagine if you grew a fingernail so long that it curved back around and went into your hand. I know that's really gross, but something like that, okay? Okay. This is the largest land animal that has ever lived, as far as land mammal that has ever lived. Let me be specific here, okay? Paracitherium. If you had to guess what animal that is most closely related to, what would you say? 20 feet tall, 25 feet long. Giraffe, right? That makes pretty much sense. It's not, though. It's not the giraffe. As a matter of fact, the living relative of these things is the rhino, is the descendant of these things. Paracitherium, the largest land mammal, 20 feet tall, 25 feet long, but you can see some of the similar kind of overlapping skin armor here, and the ears, and the facial structures that they have in common with rhinos of today. Okay? Long before there were cats and dogs, okay, now turn around and push them the other way. Long before there were cats and dogs, the animals that filled those niches were called mesonychids and cryodonts, okay? So here we've got a couple of pictures of these things, okay? Mesonychids and cryodonts. Think of it as if a wolf and a tiger were combined into one animal and stood about 6 feet tall and about 10 feet long. That's the kind of nightmare that we're talking about here, okay? So these eventually would go on towards the end of the Oligocene, or towards the end of the Paleogene, would actually end up diversifying into our modern groups of cats and dogs. Both of those groups came from these guys right here. Now, I talked a lot about what mammals were doing during this post-dinosaur era. How they filled the niches left behind by the dinosaurs. But they weren't the only things trying to. There was one group of dinosaurs that survived. I've mentioned this before. What was the one group of dinosaurs that survived the extinction? Huh? Birds. Birds are dinosaurs, okay? They are a group of avian dinosaurs is what we call them. They have that hip structure, okay? They have a lot of those characteristics. They are descendant from smaller velociraptor-like dinosaurs, okay? So they survived, and they tried to pick up where their cousins left off. So we get some very large terrestrial birds, flightless birds, that got very big. I'm talking 8 to 9 foot tall giant birds with giant beaks that would stomp around and eat those little horses I talked about earlier. Okay? There were some that were obviously carnivorous, but then there were others that would eat seeds and berries and nuts and stuff like that. Okay? But we call these the terror birds of the Paleogene. Okay? For that period of time, those maybe 10 million years or so after dinosaurs, it was kind of a toss-up. Are the mammals going to get bigger faster, or are the birds going to win that race? And it was close for a while, but in the end, the mammals won. Good for us. Otherwise, there might be gigantic birds covering the surface of our planet instead of people and other mammals. Okay. Primates. We belong in the group primate. The first primate that we know about in the fossil record is 55 million years old, but it was tiny, itty bitty, like fit in a teacup, sort of small, okay? And it looked something like this. Just tiny little primates that would wander around in the trees and eat their berries and maybe small insects, okay? Omnivorous, as far as we can tell, okay? We don't start seeing the larger monkeys like what we're familiar with. Hey guys, hey Liam, hey. Okay, we don't start seeing the larger monkeys like what we think of when we say monkey until later on in the Oligocene, okay? And then they take a hit from an extinction that happens there, and then they come back in a big way later on. Okay, so let's talk about our climate. there is a transition event between the Paleocene and the Eocene. Careful. There's a wire there. We can't push past that. Okay? You got to turn around and go that way. There we go. Okay, so right here, between the Paleocene and the Eocene, there is this spike. A Paleocene-Eocene warming event is what we call it. Okay? And then during the Eocene, there is a climactic optimum. So on the scale, by the way, the higher up you are, the warmer the climate is. Okay? So this spike right here represents a massive increase of heat for really quickly through time. And it's still a little bit interesting why that might have happened. The best thing we can tell is that this spike happened because the sea level, the seabeds were rising due to tectonics. Where there had been very deep seawater for hundreds of millions of years, all of a sudden, thanks to tectonic activity, it's getting pushed into warmer, shallower water by tectonic activity, right? And this has an effect. During those hundreds of millions of years, methane that had been generated in the ocean or that had been taken from the atmosphere and incorporated into the ocean had collected as solid methane crystals at the bottom of this deep sea, this deep ocean. Now that this deep ocean has become shallow ocean, these methane crystals are dissolving and methane gases are being released from the ocean and other bodies of water that they collected in. With an addition of methane into our atmosphere, what happens? Methane is a what? Greenhouse gas. Bingo. So with all this greenhouse gas entering the atmosphere, we believe that that is what contributed to this massive warming spike right there. Isla, no running with him. No running while you're pushing him in the chair. So then after this spike event, we get it kind of drops again, and then we get more of a consistent height of heat. It never really actually goes back to how hot it was here. Okay, we've never actually been that warm since, at least not yet, right? But this is a very warm period. Okay, so very little glacial activity during that time. We call it the early Eocene climactic optimum. Then it drops back down into the middle Eocene. We get another spike here, presumably because of another spout of greenhouse gases. Okay? And then it drops again, and then we have the beginning of the modern Ice Age and the extinction that comes with it. Here we have, between the Eocene and the Oligocene, an Ice Age event. Okay? And that Ice Age has never actually technically stopped. We are still technically in it, because the definition of an Ice Age is when you have ice at both poles of the planet. And there has been ice at both poles of our planet since this one began. 30-something million years ago. Okay, I think that's 33 million years ago. Okay? So, we have had, however, glacial transitions. Okay, back and forth. Okay, so tectonically speaking, this is what our Earth looked like during the Eocene, which you remember is in the middle of the Paleogene. Okay? So we have all of our modern day continents with a few different changes. We don't have all of Africa exposed yet. North America and South America are not touching each other. Australia, you can probably on a clear day still see Tasmania from mountains on Antarctica, on the coast of Antarctica. Okay? So Australia still hasn't moved that far away. India hasn't come to kiss the Eurasian continent there. And there's still a massive inland sea in the middle of the Eurasian continent. Okay? It's still warm here. We have not yet moved into that Eocene, Oligocene Ice Age yet. So now we see the continuation of the Laramide orogeny, which began in the Mesozoic. Okay, this is Cordilleran, so it's along the west coast. This is the one that contributed a lot to the formation of the Rocky Mountains. Okay, so this is a thrust belt. So forces from that direction, from the west, pushing into North America, are causing gigantic thrust faults to form. Remember, a thrust fault is a very low angle reverse fault, where one side is being shoved over another side, except it's between layers of rock instead of through them, which is why it's a much lower angle. But because it's a lower angle, more rock can get thrust because less gravity is being fought by that force. Okay, so more distance is covered by all that rock. And so all this rock is getting shoved further to the east from the west, making our Rocky Mountains that we have now. The Taos cratonic sequence occurred between the Paleocene and the Oligocene. So remember, a cratonic sequence is when you have ocean, basically marine sediments being deposited on top of continental sediments, okay? So you're getting a massive depositional sequence as part of this cratonic sequence. Remember how I told you, or I showed you how much of Eurasia was covered by water during this time? Well, a lot of North America was covered by water as well. Hey, Isla, can you please take my sunglasses from Liam? He shouldn't have those. Okay. Thank you. Liam, give those to Isla and she can put them back. Thanks, Bug. I go through 3 or 4 pairs of sunglasses a year because they get their hands on them. I just get like the $10 fishing glasses from Walmart, but it's still annoying to have to buy them all the time. Okay, so as part of this in North America, though, the Mississippi embayment was completely flooded. Okay, so all the way up to and past Memphis, Tennessee was underwater, where the Gulf of Mexico is now. It basically went all the way up here as well. Imagine Memphis, Tennessee under salt water. That's the way it was during this time, during this cratonic sequence. It deposited all the sand that is here now. It's notoriously difficult to have agriculture in the Mississippi embayment, historically, because of the quantity of sand there is there. And it was deposited there partly because of this event, this Taos cratonic sequence, but also the deposition of sand by the Mississippi since then. Also during the Paleogene, we see the development of the Rio Grande Rift, very relevant to you and me, because we're not that far from it, right? We're right here on the map, as a matter of fact. This is the Rio Grande River, flowing through the Rio Grande Valley, which exists because of this rift sequence. Remember, a rift is when a divergent plate boundary is forming beneath a plate. And it's the forces of convection pulling in opposite directions. Isla, please don't push him that hard. Okay? Are causing a thinning of the plate as those forces are pulling, stretching it apart until finally it cracks through the middle and magma can come up and fill it in with mafic rock, like basalt. And then all of a sudden you've got ocean crust there. Yes. Yes, Isla. Liam is fine. No. Liam, what do you need? What do you need help with? I'm not going to push you. I have to teach. Isla can push you. Isla, push him gently, please. So what's happening here is that effect. The Rio Grande River is here because that valley is here, and that valley is here because of these divergent forces thinning the crust there. Now, it is for this reason that I believe we have all of the tectonic activity, earthquake activity in the area. Now, let me preface that, or put a little asterisk on that. The tectonic activity, as in the earthquakes, are happening most likely because the data does show it is tied to fracking activities. But fracking activities cannot make faults. That's not part of the physics at play. All they can do is introduce some fluids to the system that cause those faults to slip. Fracking cannot make faults, and it cannot add stress to them. Okay? That's happening naturally, I believe, as a result of this tectonic activity here. Because this is still widening out. Eventually, the Gulf of Mexico will extend up the Rio Grande Valley into North America. Right here. Possibly even further. Okay? And then another thing that happened here was 36 million years ago. A giant asteroid landed on the east coast of North America, right where Chesapeake Bay is now. As a matter of fact, Chesapeake Bay exists because of the presence of this crater. This crater made a low point out here on that east coast. Take a look at this. Do you see this? This spike here? This is a cross-section of the crater, by the way. This is all the sediment that's been put on top of it since it was hit, since it landed. Okay, so this is the crater, and then this is the center of the crater. Do you see this spike of rock here? This is all our crystalline basement, all the stuff that was there that got hit by the asteroid. Why would that spike be there?
You want this or this? This? No, this. This? Yeah.
Did the asteroid split into two?
No. Nice thought, but the asteroid did not split into two. You're seeing a cross-section of a generally roundish crater in the middle. Have you ever dropped something into water and it goes bloop, and then some of the water goes bloop, and then comes back down? You get the bloop and then bloop. That's very technical language, right? Okay, well that bloop that comes up, that's what you're looking at here. The rock instantly melted and then bloop, upward, and then got frozen there, re-solidified in that spike. Imagine if I dropped like a rock into a pool of water, and you get that crater out, and then the water comes rushing back in and bloops upward, and then I instantly flash froze it right there. So I get that spike of water suspended there, stuck there. That's what you're looking at, except it's rock. Okay. So because of the presence of this crater, it filled in with all the sediment from around the sides, made a low point, and then all the sediment got deposited on top of it. But as this sediment deposited on top of it, this breccia inside of the crater slowly compacted. As it compacted, it made space on top. As it made space on top, it allowed the presence of normal faults to form through compaction. And these normal faults, as these blocks of rock fell down further into the crater, made a low point that turned into Chesapeake Bay today. Okay? Any questions about the Paleogene? No? Well, let's keep on moving to the next lecture. The Neogene.
Dad,
Yes?
I have to get Neon down.
If he doesn't want to get down, he doesn't have to get down.
But there's the bag.
Is there a bag under the chair? It's okay. Just good. Okay, so the Neogene is composed of the epochs called the Miocene, Pliocene, and Pleistocene. Okay, what happened? Liam, please don't kick. You can play somewhere else if you want. You don't have to play next to his feet. Yeah, you can go be over there. Okay. She's going to take him with her. Seems beside the point, but okay. Okay, so the Neogene goes from 23 million years to 11,700 years ago, which remember, 11,700 years ago was the end of the last glacial maximum. Okay, so that's where we're going up to. During this time, our whales go from being these giant, vicious, toothy predators. I mean, we still have those, right? We still have sperm whales, orcas, and dolphins today. But they diversify from just being those to a new type of whale called baleen whales, okay? Straining whales. The kinds that have the baleen, or the weird kind of sifting filters instead of teeth, okay? We see those. I told you not to push him that hard. Okay. Is your face okay? Are your hands okay? You can be in timeout right here. No, you can be in timeout. It's okay. Give me a second here. That's a weird noise. No. Okay. Like humpback whales and gray whales. Okay. Hey, do you want to help me teach? Do you want to look at the whales? Yeah, you like the whales? No? That guy, he's got a really long mouth. Okay. Some big developments that happen in the plants because we are moving from the Oligocene Ice Age, so it's a lot colder now, right? Our plants have to diversify. They have to change and to accommodate that. We're going from very warm, very widespread tropical conditions to very cool and dry conditions during this time, okay? So that means our grasslands start getting a lot bigger. Not only do we start seeing more grasses and different kinds of grasses, we see the development of these things called herbs. Now, when I say herbs, you're all going to think of something like oregano or basil, especially if you happen to like cooking, okay? Hey, it's okay. It's okay. Lay down on my shoulder if you want. Should I put you down? No? Okay, but if I'm going to hold you, I need you to calm down, okay?
No.
I can put you down or I can hold you. What do you want? You want me to hold you? Okay, I need you to calm down so I can talk, okay? Okay. All right, so herbs are not just spices, okay? When I say herb, what I'm talking about are a new group of non-woody but very hardy sort of plants, okay? Most weeds, what you and I consider today to be weeds, those ones that are ridiculously hard to get rid of, those are technically herbs, okay? They developed during this time because they were so difficult to eradicate. They survived very well, okay? And now, for some reason, they seem to survive the herbicide, which I put down. Have you heard that term before, herbicide? That's weed killer. That's why we call it that, because these plants are technically herbs, okay? So, there's another change that we see in our plants, in our grasses specifically, and in plants that come later on from those grasses, called phytoliths. Phytoliths are tiny little silica nodules that grow inside of the blades of grass. Now, what possible advantage could that have? Imagine that you are a clump of grass. What is the biggest threat to you? Yeah, something that wants to eat you, right? What's the best way to stop things from eating you? Well, you're a clump of grass. You have no knowledge, you have no intelligence, you have no independent way of thinking. But what you do have is a lot of you, and a lot of you that are experiencing mutations. The more individuals of a species there are, the more likelihood there is for mutations to develop that are positive or negative, right? But a positive mutation might be the development of these silica nodules in your tissues, because it's very difficult to chew something that's harder than your teeth, isn't it? Any of you guys ever tried chewing rocks before? I once found a tiny little screw, like a miniature wood screw, in a floret of broccoli I was eating. It was not a pleasant experience. My teeth found it, and it was painful. You cannot chew things successfully that are harder than your teeth. Well, so when you're a clump of grass with these silica nodules, right, and an herbivore comes to eat you, it's going to be able to eat a whole lot less of you before its teeth wear away. And then just like with those multituberculates that couldn't grow their teeth back, once the animal's teeth are gone, it dies off. And so this became a positive mutation in the grasses, the development of these phytoliths. Okay? These silica growths inside of the grasses became advantageous to the grasses. You need juice? Your juice is over there in that corner, okay? Go get it. I'm not going to take you. I need to stay up here and keep teaching. But you can go get your juice over there. Okay, well, that's up to you. Okay, now we do see a response to this in the herbivorous animal population a little bit later on. We'll get to that in a moment. Also, we see the development of C4 plants. How many of you have taken plant biology courses before? Anyone? Okay, so there are a couple of different types of plants. Okay, the ones that we care about right now are C3 and C4. There's another type, which for some reason I have a hard time remembering. Yes, my love. That's okay. That's okay. As long as it doesn't hit anything with it. This third type of plant, why can't I remember what it's called? Pineapples are in this group. They absorb, they do photosynthesis slightly different. In a C3 plant, though, you get your plants that breathe in the gases from the atmosphere, okay? So they take in the carbon dioxide, they break it apart in this cycle, and then they expel O2 and water vapor. Isla, are you going to push him anymore? Do you promise? Then you can get out. Liam, do not touch any of those. Liam. All right, Liam and Isla, I need you both to go back to your corner, please. Liam, hey, go back to your corner, please, or stay by the door. Thank you. Okay, so that's how a C3 plant works. With a C4 plant, which we see showing up here in the Neogene, it's a little more complicated. Okay, it goes through a couple of other different types of cells. It still ends up expelling the same kinds of things, but it's far more efficient at keeping certain things in. Okay, because it goes through a little bit more of a complex framework of ingestion. Okay, so kind of think of it as an engine versus a hyper-efficient engine. Have you ever seen like a car that says this is a hyper-efficient, fuel-efficient engine, right? 43 miles to the gallon instead of 20? That's what I'm talking about here. So just a more efficient engine, so to speak, in your C4 plants. So they become very successful. We see them going everywhere. Corn, for example, is a C4 plant. Corn is very easy to grow in most places. Okay? So, like I was talking about earlier with those phytoliths and grasses, we see a side-by-side development, a response, if you will, in animal populations. And this is another example of how we often see these two things coincide with each other, like with the development of flowering plants and the development of pollinating insects, and how they affect each other like that. Okay? So a response in the herbivorous animal population to the phytoliths in the grasses was growing taller teeth. Because if my teeth are longer, if I have more teeth to grind through, then I'm going to live longer. And so a random mutation for taller teeth became very favorable. So this is what the climate was looking like during the Neogene. Right here, by the way, this is the last glacial maximum. So this is actually during the Paleocene, or the Pleistocene, excuse me. This is what it would have looked like during the Pleistocene. Okay? And this is what it looks like now. And you can see the different bands of color represent different plant ecosystems, okay? Different environments. So this big, thick band of orange right there, that's desert during that last glacial maximum. All of this desert with a bunch of ice in the middle over here in the Himalayas, okay? And then we still have a lot of that desert here, but a lot of it has become a lot more temperate since then, okay? A lot of North America was dry, Serengeti, grassland, deserty, okay? Much less of it is so now. Same with Australia. We can tell all of this stuff, A, because of the fossils, B, isotopes, but also a growing field for figuring all this stuff out is actually pollen. Because we can figure out what type of plant pollen came from, because this is recent enough that we can compare modern pollen to past pollen fossils, then the presence of pollen in a specific location tells us that a certain kind of plant was living there, and that can give us clues as to what the environment looked like. Food chains play a big role in how adaptations and radiations move forward through time. So just like when plankton go extinct, and then the fish that eat them go extinct, and then the fish that eat those, and then the sharks that eat those, and these cascading extinctions occur, cascading radiations can occur as well. So if there's a development in my grasses, that's going to result in a development of the things that eat my grasses, and then the thing in the development that eats those, and then the thing in the development that eats those, cascading up the food chain as well. Okay? This is true of plants and of animals. In the Neogene, we see a lot of large animals forming the basis of a lot of our animal ecosystems. We see far fewer odd-toed ungulates, like horses, and a lot more even-toed ungulates. Okay? Those pigs and bison, for example. when Europeans first came to North America, there were vast herds of bison, estimated to be millions of animals. Okay? Gigantic herds of them. And then they almost went extinct, right? Because of human actions. We've talked about that before. But my point is they were very successful from this point forward. The first bears show up, by the way. Okay? During this time, as far as we can tell, is when the first bears show up. This is when the first fossils come from. We already talked about the phytoliths. This is what a grassland sort of ecosystem would have looked like during the Neogene. We've got goats, we've got sheep, we've got horses, we've got woolly mammoths, we've got bears, we've got lions. There were lions in North America. There were camels in North America. Okay? All these things have gone extinct. Not all of them, but a lot of them have gone extinct due to reasons we'll talk about in a little bit. Let's talk about the monkeys. There are two groups of monkeys, New World monkeys and Old World monkeys. New World monkeys are those that originate in South America. Hey, Isla, Liam. Isla and Liam. Isla and Liam. Shh. Old World monkeys are those that originate in Africa. Here's an interesting question. Africa and South America have been separated from each other for a very long time at this point. The oldest primate fossil that we know of is 55 million years old. And yet, Africa and South America have been separated from each other since long before the dinosaurs went extinct. So why are there monkeys in both continents? Very interesting question, isn't it? There's got to be a link somewhere. A land bridge across which things traveled. Well, it's possible, but there are no fossils across any bodies of land to prove that there were. It's not to say that there wasn't. There just isn't any evidence yet. What about a raft? It is well known, it is documented that animals, including monkeys, have rafted across giant stretches of ocean between bodies of land. For example, Madagascar. Madagascar has lemurs on it, for any of you that have watched the movie, right? Those lemurs originated on the mainland of Africa. We know that they only showed up on Madagascar a couple 100,000 years ago, if my memory serves. They got there on a raft. Some giant wooden tree, or some giant tree that got blown into the ocean, okay, maybe by a giant storm, had some lemurs on it, and those, maybe a week or two later, they washed up on the shores of Madagascar. Well, those lemurs are now extinct in Africa, but they are thriving in Madagascar. But they didn't evolve there. It's possible something like that happened between Africa and South America, but that's a lot more ocean to cross in a raft. So it's still a little bit of a mystery as to how there are monkeys on both continents that have been separated for so long. And yet, there are. The ones in South America tend to be smaller, have very, very different style tails, much longer fingers, different facial structures, but there is no denying that they all come from the same primate ancestor at some point. Now, at this point, I need to reiterate a statement that I made earlier in the semester, that nothing I teach in this class, yes?
I saw an article, well, I didn't actually read the article, but I saw an article where there was like a sunken continent somewhere between South America and Africa or something.
A sunken continent? Not that I've ever heard of.
Scientists found a sunken continent.
That sounds like one of those headlines that are just written to get you to click on it.
Okay.
Something like a sunken continent? No. That's something that would have been known about a long time before. But there are definitely stretches of that part of the ocean that are shallower than others because they're like basalt plateaus and the such. Nothing like a continent, though. No, a continent is a large enough landmass that it would be really close to the surface, right? Even if it was all underwater, it would be a lot closer to the surface than the bottom of the ocean is. So that it would be a well-documented fact. It wouldn't be something that scientists just discovered. We've known enough about the bottom of the ocean that we'd have known about that for a long time, right? Okay, so I'm just gonna continue where I was leaving off. Liam, what's wrong? You can't get up? Are you stuck? Did he go behind the case? You're not stuck. You were just behind the curtain, silly goose. You want to be up here with me? Okay, nothing that I teach you in this class is meant to persuade you or dissuade you from any previously held beliefs, religious or otherwise, okay? But I will tell you from this point in the lecture forward, we are discussing human evolution. So whatever that means to you from any personal beliefs is completely up to you. I'm just going to teach you the science as we know it now. As we understand it now, I should say. Know is a strong word. Understand has a little flexibility because what we understand could change in the future. Okay? So, evolution of the human family starts about now, here in the Neogene. Okay? We belong in the superfamily Hominoidea, excuse me. And it's difficult to prove that there is any link that goes further back than the Pliocene to this superfamily, okay? As far as we can tell, the Pliocene is when they first start showing up, okay? The earliest fossils of apes, which are our close relatives in Hominoidea, okay, is in the Miocene, so way further back. During the Paleogene is when the Miocene was, right? But our specific ancestors, as we understand it, around the Pliocene is when they show up. Now, a very important thing that happened here in the progress of human evolution was the collision of Africa and Eurasia. You remember we were looking at that map of the Middle Miocene before? Okay, or the Middle Eocene, excuse me. And Africa had not run into Eurasia yet. Well, now it has. It's collided here during the Neogene. And as that's happening, this allows the passage, the migration of animals from Africa into Eurasia, the collision of two wildly different ecosystems. Man, what a strange thing that must have been. For these two continents to finally become close enough that animals can start migrating from one continent to another. The mixing of two groups of organisms that have not been around each other, or have never been around each other, for tens of millions of years. Hundreds of millions of years, actually, since the breakup of Pangaea. Okay? So two very different ecosystems colliding. Okay? Part of this collision was the migration of hominid primates from Africa into Eurasia. And we'll see how those different groups interact with each other later. There was an extinction in the Miocene thanks to temperature changes, okay, some environmental changes. Only two groups that we know of in Hominoidea survived. Gigantopithecus, which were these guys. If you've ever heard of the stories of the Sasquatch, people often pattern them after Gigantopithecus. Okay. 8 foot tall, big, brawny, walked up on 2 feet, had social communities because we find their bones together all the time. Okay. And one other mysterious group that we can really only say was probably some kind of gorilla. They survived just barely through this extinction. In a tiny little pocket forest. Let me go back and show you. Take a look at this. Okay? Here in Africa, right here and right here, those are the only groups of rainforest that these hominids survived in. Okay? Hominoideans, I should say. Those are the only two tiny groups in Africa that they survived in during that glacial ice age. Okay? Hey, share it, please. Okay? So we still know very little about this other group of hominoideans. For the longest time, we thought it was only Gigantopithecus that survived, but there's other evidence now. Okay? Moving onwards, through the Miocene extinction, There are a whole bunch more groups that show up, okay, including groups that start to more closely resemble us. Isla, I'm going to take it away if you can't share. Thank you. Okay, so different groups start showing up. You can see as time goes on, we start to have more and more evidence of these groups. More and more complete bones. Look, we only have a few bones of this one, but they get more and more cohesive, more well put together through time. We find more and more bones of them. For the longest time, we could not find a direct link between these long before human ancestors and the more recent ones that we were pretty sure were human ancestors. There was a couple million years of link missing. But not long ago, meaning a few decades ago, they discovered a new species called Sahelanthropus, which represents what we call an intermediate genus. Okay? So it has characteristics of both the apes and the genus Homo, like us. Okay? You have to play with this in the corner. Go play with it in that corner, please. Here's the lid. Go play with it over there. Okay. So you can see it's got this gigantic brow structure similar to what a gorilla does today. Many other species of ape. Okay? But also, look at how flat the face is. Okay? Very flat face, very human-like nose, eye sockets, teeth, very similar to what humans have today. So this and several other species share characteristics of both the apes, the gorillas, and humans. Modern humans. So this is what we call an intermediate genus, okay? Now, Australopithecines come after this, okay? 4 million years ago are when we see the first Australopithecines, and this is what they would have looked like. Australopithecus, okay? So here's an Australopithecus skull, and then here is a human Homo erectus skull, which was one of our near cousins. Do not touch, Liam, Liam, Liam. I told you not to touch. No, I told you not to touch. Liam, do you need to go in timeout?
No.
Liam, please don't touch those. I told you to stay in the corner. Go into the corner. Go to the corner. I'm sorry.
Oh, look, a skeleton.
It is a skeleton. Good job. Okay, this is an Australopithecus skeleton. Notice that they were obviously capable of standing upright, but what about their arms? No, tell me what's weird about their arms compared to ours. They're super long. Yes, Isla?
I don't know.
You don't know? That's fine. Okay? When you stand up and you put your arms straight down, they go maybe halfway down my leg to my knees. Look at this guy. He could scratch his knee without bending over. Right? Yeah, I know. That's weird, right? I have to do this. He didn't have to. He just, right there. Very long arms. And long fingers, by the way. Perfect still for climbing. They obviously were still good at climbing. But they were obviously also capable of standing upright. And look at their hip structures, by the way. Almost identical to a modern day human. Yes?
Dad,
Yes?
I can't see skeleton's eye.
Well, skeletons don't really have eyes, Bug.
Oh.
They're missing them. That's kind of the point.
Oh, look.
Yeah. Okay, so we start seeing characteristics much closer to humans in Australopithecus, okay? Now, 2.4 million years ago is when the first genus Homo starts showing up. So from Australopithecus, we've gone forward 1.6 million years, and now there is a new genus that has shown up, which we call Homo, okay? This is the one that we belong to. Our genus showed up 2.4 million years ago. And one of the defining characteristics of this genus is the ability to use tools. So they had smaller, more specialized teeth than Australopithecus, closer to us, okay? Larger brains. Liam, all done. All right, I'm going to take it away, buddy. Then please stop hitting things with it. Okay. But they also made tools. These are tools that are almost 2.5 million years old. Yes, they don't look like it until you look at the fact that these are rocks that are chipped in very specific shapes.
Dad,
Yes, my love.
what's this called?
This is a tool. It's a rock that's been chipped into a shape. They also did this with bones, okay? But they would chip them into these shapes for scraping meat off of animal hides, for cutting, okay, for grinding, okay? So they had all of these abilities, and they obviously had the intelligence to figure out how to make these things. She's just going to go around the room maybe. Okay, 2 million years ago is when we see Homo erectus. Okay, Homo erectus lasted for quite a long time. They went from the Africa, Middle Eastern area and immigrated out into Asia. Okay, this is the first major migration, as far as we are aware, of intelligent, yes, not as intelligent as us, but remember that's kind of a moving scale there. Intelligent primates moving into Asia. Okay, so they died off there, and we thought they died off about 800,000 years ago. So they were there for more than 1 million years, spreading out. We thought that this group died off 800,000 years ago, but recent discoveries have shown that there was actually an island out in Indonesia that they were living on until only about 100,000 years ago. Much, much longer. So they died out in the mainland, but survived on at least on this island, possibly on other islands as well. But the cool thing about this group is, this group of hominids actually got very small. We call them pygmies. Have you ever heard that term before? Pygmy? Why would that happen? Knowing what we know about adaptation. Hey, Isla. Shh. Knowing what we know about a positive adaptation environment, what would be positive adaptation on a small island with minimal resources? Isla, please leave the camera alone. Let me put it this way. If I am a 6'2" giant of a man, built like a football linebacker, okay? I'm just a big dude, right? How many resources do I consume versus someone that's 3 foot tall? I consume a lot more resources. So on an island with a small amount of resources, cut off from every other island, a positive adaptation is going to be for smaller body size, and larger body size is going to be a negative adaptation. You following that? And so as time goes on, smaller body size is favorable, and this community on this island becomes smaller and smaller body size until they become the pygmies. Okay? Very small groups of people, between 3 and 4 feet tall. Okay. So they also use lots of tools, by the way. These are all tools that have been found from this culture that were chipped into those shapes to be used as tools. Okay. So we can see that there's an increase in body size as time goes, or brain size as time goes on. Brain to body ratio is huge. Brain to body ratio is a defining characteristic of our genus. Okay, why we have the intelligence that we do. Why other animals like dolphins do as well. They have a good brain to body ratio as well, as do orcas. Okay, so this is the size of a chimpanzee. Okay, this is the size of a human at birth. Okay, their brains. This is the size of a 1-year-old child, and this is an adult human. This is an adult Australopithecus. So an adult Australopithecus had a brain about the size of a human baby, which is why they were probably able to figure things out like, I can use this rock to do this thing. Babies do that all the time, right? I'm going to pick up this thing, put it in my mouth, enjoy it in my mouth for a little bit, and then I'm going to throw it at you, right? They know how to do basic things like that. 1-year-old children can do a little bit more. They have a little bit of logic, okay? Adult humans are capable of building machines. There's a tie here. I'll just make this note really quick. Did you have a question? No? Okay. Yeah, you had a question. Okay.
So Flintstones is very inaccurate.
Oh, Flintstones is super inaccurate. Aren't there dinosaurs in Flintstones? Yeah. No. What was I saying? Oh, okay. So here is an unfortunate, or maybe a fortunate side effect in some ways, of the larger brain-to-body ratio. Larger brains mean larger what? Heads, which, as any woman who has given birth knows, is not so fun, right? So this was the trade. We stopped having, for the most part, larger groups of children for every birth. There are still occasionally twins and triplets and very rarely larger groups of births than that. But for the most part, we give birth to one young at a time, whereas a lot of other mammals give birth to multiples. Think dogs, cats, rats, mice. Okay? Give birth to larger groups of children at a time. Very common. Along with the larger brain came a lot more strain on the mother. And so a positive adaptation was just having one birth at a time. Otherwise, the mother would quickly die off from the stress and the physical destruction of that process. Larger brains, larger heads, less births over a given time period. Okay? That traded off in the end. Normally, that would sound like a terrible trade for the continuation of a species, but our intelligence gave us the ability to survive better as we got older. Okay? All right. After this, we see the development of Neanderthals. Okay? Neanderthals settled northern Europe hundreds of thousands of years ago. Between 400,000 and 600,000 years ago, I want to say. About there. There's some disagreement about that, but they were definitely there at that time. As to when they first started, still not sure about that. At least I'm not. And I haven't seen any firm evidence to suggest otherwise. Okay, now, there's a lot of misconception that the Neanderthals are the direct ancestors of humans. They are, in fact, not. They developed at the same time as our ancestors, which I will get to in a moment. Neanderthals settled northern Europe, and as far as we can tell, again, bear in mind, this is a non-human, non-Homo sapien related species. It's more like a cousin species, okay? Our ancestors are still in Africa right now. The Neanderthals developed up there in northern Europe completely independent of us. And they had art. And they had culture. They had, it would seem, some concept of at least morality, possibly even religion. They buried their dead with gifts. They buried their dead with flowers and with food and with tools. Yeah.
These are the ones that did all those cave drawings that are like thousands of years old.
Denisovans?
France and stuff.
Yeah, the Denisovans. I don't talk about the Denisovans here, but they are another group very similar to what happened with the Neanderthals, except they were in Middle Europe and out east as well. Okay? I don't really talk about them here for the sake of time. Neanderthals the story of the Neanderthals kind of covers the story of the other smaller groups similar to them. Okay? But there were other groups like this that developed independent of Homo sapiens, and they had some amazing characteristics here. Like I was saying, they had empathy. They would bury their dead, first of all, which is incredible, and then they would give gifts to their dead as if they had some kind of understanding of, we missed this person, we loved this person, and we want them wherever they're going next to have something nice. Which may be evidence of some kind of religion. Very fascinating in a species not our own. Okay? And then, of course, we got to talk about us, Homo sapiens. The first evidence of Homo sapiens moving out of Africa up north was about 150,000 years ago. Okay? Now, they came with a much larger brain-to-body ratio than any of their cousins, which means that they had more tools. They had more understanding of how to use those tools. They came with wooden tools, and it wasn't that long before there was evidence of metallurgy taking place. They had art. They had music. They even knew how to make some forms of rudimentary armor. Okay? Now, it's no coincidence that at the same time that Homo sapiens showed up in Europe, moving out of Africa, Neanderthals and Denisovans and all those other smaller groups died off. More likely than not, due to the fact that Homo sapiens showed up with weapons and armor, it's most likely that those other groups were conquered. However, not all of them were killed off, as evidenced by the fact that we can go through our DNA and find little bits of DNA with Neanderthal in it. I've done my DNA profile. I have a very small amount of Neanderthal DNA. My wife says that's where my massive eyebrows come from. Yeah. But I've got it. A ton of other people have it. As a matter of fact, anyone that has Northern European ancestry probably has some small amount of Neanderthal DNA, which means that at the very least, some Neanderthals survived the conquering, and whether that means they were taken as slaves or whether it means they were incorporated into the culture, I don't know. But at the very least, there was some interbreeding going on there between the two different groups. Yes?
How does it show up on your DNA test? Does it say Nia?
Mm-hmm. Yeah. Yeah, you can do 23andMe, you can do any of those tests, and they can test for Neanderthal DNA. Yes, my love? Liam, what do you say? Good job. Okay. So there is art from Homo sapiens going back 120,000 years. And, pigments meaning like painting, right? And then there's art like carved flutes and stuff, and that carved horse going back 40,000 years. Okay, so we've been at this for a while, it would seem. Yes?
Is that why the North Sentinel Island leaves on that island? Because of the migration?
The what? I'm sorry.
You heard of the North Sentinel Island?
North Sentinel Island, what's on there?
There's these like tribes of people where they're the only like humans that are outside of our like technology. They're like
Oh, they're not the only ones. No, so there are people on those islands. There are people in the Amazon. There are a few groups of people who have never encountered modern society. And as soon as we know that they exist, United Nations and several other groups work very hard to keep everyone else away from them. Because along with the exposure to the technology comes exposure to other things, diseases, right? The politics, ravages of modern society that you and I take for granted, right? You introduce high fructose corn syrup into that society, and all of a sudden everyone gets upended, right? Everything goes nuts. So there are a few places around the world that have societies that are not encountering us, and that's at this point that's orchestrated, that's designed that way. I think sometimes how interesting it will be when one day those people figure out that we are here, right? That those weird things that they saw flying through the sky, because you can't keep planes away from them. You can't keep them from seeing things like planes. At this point, who knows what they think those are? But someday, inevitably, these people are going to figure out that for hundreds of years, everyone else in the world kept them in the dark. And I got to wonder what that'll be like for them. It'll be interesting.
It sounds like the Egyptian drawings that look like airplanes and stuff.
Oh, I see what you're saying. Yeah, exactly. Yeah. Fun things like that. Fun thoughts like that. Maybe there's a whole mythos in that society of what airplanes are. Maybe they think that it's one of their gods coming to take a look at them from the sky or something. Or a giant bird that lives in the next valley over. Knock, knock. You're not going to get out. Okay, let's talk about the climate. We got to keep moving. Okay, so at the beginning of the Neogene, it was pretty warm. This is post-Oligocene Ice Age. Okay, so we're in a warming trend. And then it cooled off in the middle of the Miocene. And then it warmed up again at the end of the Miocene. So we have this constant fluctuation back and forth from this point forward, but always with these ice caps at the top and bottom, meaning that we are still technically in that same ice age. Okay? We track this through the development of siliceous and carbonate oozes, which, remember, occurs, you get those siliceous oozes when our water is cold, and we get our calcareous oozes when our water is warm. And so we can see in the fossil record, is there more silica-based exoskeletons or more calcite-based exoskeletons, okay, in our life forms in the ocean, and that can help us kind of track that. Also, the spread of C4 grasses happened a lot during these warming trends, okay? And then we get the development of this Panama land bridge right here between North and South America. And then we see another migration of these two ecosystems back and forth with each other, which is why we see things like different types of sloth in both places. We see mammoths in both places. We see certain types of lions and pigs in both places from this point forward. From the mid-Pliocene all the way through to the Pleistocene is what we typically refer to as the last ice age. But really, what you and I know now is it's still the same ice age. It's just the last glacial maximum. Okay? So during that glacial maximum, this is what our northern hemisphere looked like. This was all one massive ice sheet, covering half of North America, a huge chunk of Eurasia, all of Alaska, moving out over here off the coast of Russia. Okay? All of that was covered in ice in the northern hemisphere. So what happened to cause this? Interestingly enough, we believe that it was tied closely to the development of the connection between North and South America, that Panama Land Bridge. Why? Well, because before this point, the Atlantic Ocean and the Pacific Ocean were able to communicate with each other and share temperature and salts. Yes? That's yucky. What is that, applesauce? Liam, don't spit applesauce into stuff. Yeah, we got to let this dry off now before we put the Play-Doh back in it. See? We're going to dry it off before we put the Play-Doh back in, okay, sweetie? See? No more spitting applesauce, okay? All right. So no longer can the Atlantic and the Pacific Ocean trade salt and temperature, warm and cold water, through this zone. It has to go around the bottom of South America, which, by the way, to get down there, it gets cooled off by Antarctica, its proximity to the South Pole, right? So this totally shook up, totally changed the whole dynamic for how warm water was shared through both of those oceans. And so what happened was the Atlantic Ocean became more salty than the Pacific Ocean as this water kept circulating around back and forth. And it could not share that salt with the Pacific Ocean. And that led to changes in temperature, which ultimately led to a positive feedback loop of more and more cold water in the Atlantic Ocean, which added to this North Atlantic ice shelf and ended up with another ice age that we had during that time. Okay?
Mom is picking up you. We have to go quick.
So, in addition to the tectonic activity that happened there that caused the Ice Age, this is the first time that we actually see a for sure tie-in to Milankovitch cycles. Do you guys remember what Milankovitch cycles are? Milankovitch cycles are the way that the Earth spins around the sun. You've got your obliquity, or sorry, your eccentricity. Okay. No. Hold on. Yes, the eccentricity. I don't know why that was escaping me for it. It's eccentricity, obliquity, and precession. Okay. The eccentricity is how ovular our orbit around the sun is. We go from a round orbit to a more stretched out kind of ovular orbit. Okay. And then we've got our obliquity, which is where we are on that angle. And we kind of go back and forth across that angle like this. And then our precession, which is our wobble around that angle, like this. Okay? So Earth is always moving around the sun like this. Okay? Here, if I pick up this globe and show you. Moving around the sun in our orbit. As we are spinning, as we are tilted at this angle, as we go back and forth with that angle, and as we rotate around that. Earth is always doing this in space. And so when we are further away from the sun and certain conditions are right, then Earth absorbs less less radiation, okay, less energy. And so we cool off and we enter an ice age. 850,000 years ago, that's the first time that we can positively confirm Milankovitch cycles contributed to this process. And it has been ever since. In addition to the greenhouse gases in the atmosphere, adding to that as well. All right. We see a reduction in the forests in the northern hemispheres and the far southern, in the northern climates and in the far southern climates as the ice is advancing, as temperatures are getting colder. So where before there was a deciduous forest, now there is a polar desert, or during that glacial maximum there is. So here's Stockholm, Sweden, Hamburg, Germany, Paris, France. So where Paris is now, there would have been tundra. Where Germany is now, was a polar desert. And where Sweden is now, it was covered in an ice shelf during that last glacial maximum. Isla, don't touch. This is what North America would have looked like. Okay, so this is as far south as the ice went during that maximum. Directly after that ice melted, all of these giant lakes existed where all that meltwater was deposited from the melting glaciers. Some of those are still there. We call them the Great Lakes. Okay, Lake Agassiz is pretty much gone. This is Lake Bonneville. Lake Bonneville has reduced to a tiny little salt lake we call the Great Salt Lake in Utah. Okay, but that once was this whole Lake Bonneville. Lake Lahontan, that's all gone.
Stay with me, Mommy. Stay with me.
Okay, so a few more important tectonic changes that happened. The Basin and Range Province formed here. Okay, the Basin and Range Province is a series of fault blocks and valleys that happen as the Great Plains, Liam, careful, as North America in the west has gotten kind of stretched out due to these tectonic forces, causing normal faults. And these normal faults separating the sides away from each other create valleys between fault blocks. Okay, so we got valley block, valley block, valley block between all these faults. Yes? What is this? Liam. Okay. I told you to stop it with the applesauce. Now you get timeout.
No.
Yes. You made a mess, and I told you to stop it with the applesauce. Now you yes, you can stay there for a few minutes.
I'm gonna kiss my sweetie so he can be sad.
Okay, that's nice of you. Okay. I did put you in timeout. All right. You good? Okay. The development of the Sierra Nevada mountain range out in California. If any of you have ever been out to California, the Sierra Nevadas are a very prominent mountain range out there. That happened during this time. Again, more collisions between island arcs, but more than that, it was volcanism. Okay, so the Sierra Nevadas are mostly made from magma chambers that were uplifted, okay, as a result of the subduction of the Pacific Plate and the Farallon Plate under North America. Many of these mountain ranges, of these magma chambers are actually Jurassic in age, but were uplifted during this time, making the Sierra Nevada mountain range, okay? And then the development of the San Andreas Fault there in California as well happened during the Neogene. We can skip past that. The Himalayas, yes.
It's Liam in timeout.
Liam is still in timeout.
That.
That's the abominable snowman from Monsters, Inc. You guys have all seen Monsters, Inc.? Remember when they go through the door and like, welcome to the Himalayas? Snow cone? Right? Yeah. Don't worry, it's lemon. Okay, so Mount Everest is the tallest mountain above sea level, right? It is about 5.5 miles above sea level, okay, at its highest point. It is not the tallest mountain on our planet. That goes to Mauna Loa.
He wakes me up
Why?
because.
Oh, you wanted to touch it?
Yeah.
Okay, Liam, you're still in timeout. Go back to the corner, please. You can come out in a minute. Okay, now this formed as India ran into Eurasia right here. Okay, mountain range Himalayas formed right there. Now notice Australia and India are riding on the same plate. Okay, they're going at the same pace, going in the same direction. When India ran into the Eurasia to form the Himalayas, watch what happens to Australia. Okay, so we're going in this direction, then all of a sudden, it takes that hard left. Why? Because its momentum was pulled away as India, riding the same momentum, hit Eurasia. Okay. We also see the development of the Alps in the Neogene as Africa runs into Europe, making the mountain ranges, the Alps, the Alpines, all of those out there along southern Europe. Okay, and those are only getting taller, they're getting larger as Africa continues to move north, Eventually, that Mediterranean Sea will be completely closed, and there will be another Himalayas-sized mountain range between Africa and Europe, right there where the Mediterranean Sea is right now. We're seeing that process happening. Okay, any questions about the Neogene? I know, this one's kind of a slog. One more, folks. One more, and this is the shortest one. Because we only have 11,500 more years to talk about. Hey, brother, we talked about 4.5 billion. Okay? Don't complain about 11,500 now. Now, granted, this is the most relevant 11,500 years to you and me. Why? Because this is when our civilization really took off. Some things that have happened over the last 11,500 years. Deforestation, agriculture, overhunting, building cities, the utilization of fossil fuels. These are some of our highlights, right? The highlights of human civilization. Some for good, some for bad. Many people would argue all for bad as far as the Earth is concerned. So this is the Holocene. At the end of the Pleistocene, 11,700 years ago is when the glacial maximum ended. Everything started melting. Everything started warming. We moved into the Holocene. Okay, new forests started growing. Okay, humans, in particular Homo sapiens, we're expanding outward. We're making more civilization. We're building cities, communities. Okay. We can chart the back and forth of the transgression of the oceans during this time by seeing the growth rates in coral reefs. In particular, a favorite place to do this is off Barbados. Okay, so by tracking through coral reefs and by tracking through forest pollen samples, we can see this is what the extent of the glacial ice was 12,000 years ago, right before the end of the Pleistocene. Okay, and this is how much land would have been exposed. 9,000 years ago, here we are, much less land because the ocean levels are rising, and then today, far less land because the ocean levels have risen to their current levels.
Excuse me, Dad.
North America was settled right before this time period, the Holocene, about 13,000 years ago, we believe, okay? Because there was a land bridge between Alaska and Russia. This green patch, this is all land that's exposed because of the presence of all the ice. All that ice is there, so sea levels are low, meaning that this is all exposed land. So people wandered across, migrated across from Russia into North America through Alaska and down into Canada and the modern United States. Now, it didn't take long at all for sea levels to rise and this land bridge to be covered, and it is still covered by water. That water is only a couple hundred feet deep on top of the former land bridge. We know that land bridge is still there. It's just covered in water right now. During the next ice age, or the next glacial maximum, it'll probably be exposed again. However, the first civilization that established themselves here, okay, we call them the Clovis people. They were making really cool, if you ever heard of Clovis heads, they're often talking about very meticulously crafted arrowheads and spearheads. These people were very, very skilled at turning chert and flint and jasper and agates and all of these quartz rocks into hunting pieces, okay? So they're most well known for that. Unfortunately, it seems like the center of their community was wiped out by a nearby strike. Okay, a small comet, an asteroid, meteorite, whatever you want to call it. Still not sure what it is, but there seems to have been a large strike nearby where their civilization was, and they kind of scattered from there. And from other groups and the remnants of the Clovis people come the groups that would show up later on and ultimately form into the Native American tribes that settled North America after that point. Okay, so along with the arrival of humans in North America, where's Liam? Oh, is he in the corner? Oh, he's right there. Okay, I heard him, but I couldn't see him. Along with the arrival of humans 13,000 years ago, started the decline of the megafauna, the mammoths, the giant ground sloths, okay? A lot of these giant animals, what was she asking you? It's very nice of her to ask that. She's like, are you okay in this class? Blink twice if you're in trouble. Okay, so they started to die off as humans showed up. Why? Give me some reasons why the megafauna might have died off at the same time.
Overeating it?
Overhunting? Sure. Any other reasons?
Resources that they took away from the animals.
Resources that they took that the animals needed. That's a good one. Okay.
Change.
Huh? Yeah, climate change. We're hitting all the major ones here, okay? Definitely they were being hunted by humans. We know that they were. What?
Stop moving.
I can't help it. You ask them. I move when I teach. Thank you. Okay, so they were definitely being hunted by the humans. Humans show up on the scene. All these animals, they have no idea what humans are. They don't run away. They don't stop you. They don't try and not get killed. That's not how they know a lion is a threat. They don't know that a human with a spear is a threat, at least not at first. So they're easy prey. And so humans, yes, they start hunting them. But here's the deal. Never, ever, ever could that few number of humans ever wipe out woolly mammoths. Woolly mammoths would never have been extinctified by humans when there's only maybe a couple tens of thousands of humans that are doing it across an entire continent. So that can't have been the only factor. Yeah?
Is that at the very end of the Ice Age?
Yes, this is the very end of the Ice Age, which means what? Bingo. It's getting warmer. So if I'm a woolly mammoth and I'm covered in fur and 12 to 18 inches of fat, I'm not adapted very well to warm climates, am I? If I put the thickest, warmest parka on each of you and then sewed it shut, and then I turned the temperature up to 90 degrees, everyone would get miserable real quick. But guess what? You can't take it off. Right? You're stuck. Well, that's what it would have been like. Now, there would have probably been some kind of mutation. There had been in the past that allowed animals, in particular the mammoths as well, to lose that fat, to not have as much hair so that they could survive the warmer trends. Okay? This occurs through random mutation. However, before they even had that chance, the few that were surviving got eaten, got hunted to extinction. Combination of their normal predators plus humans and the climate change, too much for these larger animals to survive. So the mammoths died off, the giant sloths died off, some of the larger species of bear died off. Liam, hey, the Play-Doh needs to stay in the corner. Okay? Isla, can you help Liam put the Play-Doh back in the corner? Because he's carrying it out here and he asked for your help. Thank you. Okay. Now let's talk about agriculture. Agriculture is far more important to you and me than you probably realize.
The answer is no.
Okay, that's fine. Hey, can you put your sweater in the corner? Put your sweater in the corner, please. Thank you.
So I will go to the top.
Don't forget it. Okay, so agriculture is the purposeful development of plants for consumption. Okay? Now, this also includes animals later on, husbandry, okay? The utilization of animals for consumption as well, okay? But let's start off just by talking about plants. Wheat and barley seem to have been among the first groups of plants that were purposefully cultivated for consumption at certain times of the year. We see the first development of this. I know it says 6,000 years ago, but what that means is it spread all across Europe by 6,000 years ago. Not that it started 6,000 years ago, so don't write that down. Okay, right here, coming out of Anatolia, which is modern-day Turkey, about 8,500 years BC. Okay, about 8,500 years BC. So at 10,500 years ago, is when we see the first evidence of this agriculture moving out and into Greece. From Greece into the Balkans, and then out into Central Europe, across to Italy, out to Spain, up into the British Isles by 4000 BC or 6,000 years ago. That's what that's saying. Okay? I've gotten some people that got that wrong. Okay? Huh?
Where did it spread from?
It spread from, as far as we can tell, modern-day Turkey. Okay, so this area down here, yes.
Wasn't there corn already in North America around this time?
Yes. Corn is a North American thing. As are tomatoes and potatoes, by the way. Those are South American. Those were not in Europe. They traveled, they came back with the explorers. But it wasn't being purposely cultivated yet. Yeah. No, that happened later on. There was definitely agriculture. Nice. Put it back, please. There was definitely agriculture in North America later after this point. Not because of this. Those people were already over there. At least some of them were. There's some evidence that suggests that people may have gone from Europe to North America a long time before BC, the time that we call BC, but it's still uncorroborated. Okay. Now, we use trees a lot of the time to understand the climate shifts that happen during the more recent periods of time. Rocks, the isotopes that we see in rocks are not terribly relevant, not terribly useful when we're talking about periods of time in thousands of years. Millions, yes, but not in thousands. And so we have to rely on the isotopes that we find in tree rings in particular to figure out a lot of the trends that happened. What was the concentration of greenhouse gases in our atmosphere? What was the temperature? What was precipitation like? What sort of wildfires may have occurred during that time? All of these are things we can figure out utilizing trees. Like this one. This is Methuselah. He is a scrub pine or a white pine, I want to say. White mountain pine, I think he is. Yeah, that is a 4,500-year-old tree. And so by studying samples of this tree, we can figure out a lot about the ways that climate changed, okay, over the last 4,500 years. The Industrial Revolution kicked off a whole new trend of climate change, okay? While the Earth was already warming up and had been for thousands of years, the utilization of fossil fuels since the Industrial Revolution has only caused it to increase. Here is a concentration, a chart showing you the concentration of CO2 in the atmosphere since the Industrial Revolution. So here's 1700, here's 2000. Check that out. That hockey stick, right? Now that's purely because of our use of fossil fuels. It was already happening, but it's happened at a much more consistent rate now. Look at this. Here's our thermal changes from 200, 600, 1000, 1400, 1800, and now. Notice how we saw a definite increase in temperature right here about 1000, 1100 AD. And then we saw a dip again. We call this the Little Ice Age, about 1600. It happened during the Dark Ages, right, is what we call that. Part of the reason why it was the Dark Ages is because everyone was suffering because of the decrease in temperature across the planet. Okay, we call it the Little Ice Age. And then since then, it was on a steady increase, and then we only spiked it up even more through our utilization of fossil fuels, pumping all of those all that carbon dioxide. Now, we have experienced between 1920 and now, over the last 100 years, a 1.3 degree increase in temperature. It's estimated that over the next 100 years, that will be anywhere from 4 to 9 degrees because of this logarithmic increase that we're seeing. Okay? That's only 75 years away at this point. So in 75 years, Earth could be about 9 degrees warmer across its entire surface. That's quite a lot. Yeah. We can actually already see the results of this melting, as there are cities like Vienna. Is it Vienna? Hold on. It's not Vienna. can't remember the name of the city. There's a city in Europe. My mind is shot right now. There's a city that is like has water in the streets. You know what I'm talking about? Venice. That's why. Venice. Thank you, Vienna. I guess I can understand how my mind went to Vienna. But Venice has water in the streets, right? And you can see people walking around in their boots with water, right? There is an island off of Panama that has completely submerged. Every building is underwater now. They had to evacuate everyone off the island a few years ago and send them off to Panama. Okay? This is becoming more and more common as sea levels continue to rise. Okay? Sea levels are rising by about 2 millimeters a year and increasing, which doesn't seem like much until you think about it in terms of 10 years or 100 years. Okay? And the rate is only increasing as melt rates of all of these glaciers are increasing. Everywhere you see that's blue, that is how much ice has melted away. Okay? So in 2002, all of that gone. This was all gone by 2000. All of that was gone by 2002. If I had a more modern graph, you'd see a lot more of that is gone now. Okay? So this is what the Holocene is characterized by. Massive climate shifts and human interaction with our ecosystems. Any questions about the Holocene? Well then, yeah.
There's been projects for like people saying they want to plant trees as many as they can. Is that gonna help it? Or?
Planting trees is nice, but a drop in the ocean, so to speak. Pandora's box is open. The genie's out of the bottle, however you want to describe it. There's no way to reverse climate change. What we can do is mitigate our involvement and work to adapt to the changes that are happening.
Do you think the next glacial ice age is going to be much worse than the last one?
It's hard to predict what the next glacial maximum will be and how what's the word I'm looking for? How bad it will be, right? It's hard to predict something like that. Hey, Liam, can you put that down, please? I thought he was going to knock over all my stuff there for a second. Yeah, hard to predict that. It might actually be not as bad as the ones in the past have been because of how bad this warming trend will be. I will tell you this, though. Everyone's so concerned about the Earth, and I understand why. We live on the darn thing. But if what you're concerned about really is the Earth and how humanity will live on it, I completely sympathize with that. People who are like, the Earth above humanity, like, save the planet at the expense of human lives, I'm like, I don't even want to associate with you, really. You know, those are the people who are like, sure, sacrifice all the people on the islands or whatever if it made a difference for the planet. I don't condone the loss of human life. There are plenty of nuts like that out there, though. Earth takes care of itself. Earth has survived far worse than us. It'll be fine. Life will succeed. If people think that in any way we have more power than an asteroid impact or a gamma ray burst, then they don't understand Earth's history. Life is still here in spite of all those things, and it will be here long after we are gone, no matter what we do to it.
Think about the polar bears.
Think about the polar bears, yes. So, I mean, yeah, we should definitely be concerned about the things that live on our planet right now and do our best to protect them. But I don't think it should come at the cost of human life. Human convenience, that can give way a little bit. I'm even okay at the expense of a little bit of our progress, our civilization's progress. Not all of it. But, yeah, things to think about.
Like the Unabomber, he didn't like the technology and all that, so that's why he was
Yep.
calling people.
Yep, every now and then you get nuts like the Unabomber. Yeah. Yeah. Yeah, I don't condone that at all. Okay, well, let's move on to our final exam review then. It's going to open today, along with your lab exam. So let's get some questions in on that. Your final exam is cumulative. Hey, Bug, you want to sit with me? Want to join me for this part? We're going to answer some questions. Okay, so it's cumulative, meaning that from lecture 1 to today, everything is covered on that. What? You need Isla?
No, I need cat.
You need a cat?
Yeah.
I don't have a cat.
A cat and a sheep.
Oh, is Isla a cat?
Yeah.
She says she's not a cat. Do you want to be a cat?
No.
No?
My name is Aya.
Yes, it is.
Yeah.
Okay, questions for the final exam review. How many questions? Hold on. I can't hold both of you, buddy. Isla, I'm going to put you down, okay? Because Liam's sad that I'm holding you. Okay? I'm going to put you down. It's okay. I need to look at something anyway. All right, go play. No, Liam, I'm not going to hold you. I told Isla that I couldn't hold her, so I'm not going to hold you either. I'm going to look up how many questions there are in here. I remember at the end of last year, I took a few questions off and kind of combined the content of those questions into a few others. So before, it was, I want to say 28, 27 questions. Let's see how many are on here now. Oh boy, they just updated Blackboard. What did they do? Hey, Isla, please leave the camera alone. No, leave the camera alone, please. I needed to look at me. All right, there are 19 questions. Now, I'm going to give the same caution here that I always give for my exams. Please make sure that you are taking the exam on a device that can open images. Do not take it on an ECISD computer. The firewall will block some of the pictures. I promise they're appropriate. It's fossil fish, but for some reason the ECISD firewall does not like them. So please take it on a home computer or on a computer at the LRC here on campus. That only applies to you if you're a high school student. Obviously, if you're out of high school, then you don't have the ECISD firewalls to worry about. Isla. Yes.
What is the last day and time to turn in everything?
Everything has to be turned in by midnight tomorrow. So Thursday, what is tomorrow? The 9th? The 10th? The 8th. Thursday the 8th. And that's because, Liam, all done. All done. Okay, Liam, all right. You need timeout? Then please stop. Levi. No, she doesn't want to be pushed. You have to respect what Isla wants. Okay, so that's because graduation is on Friday, and I have to have all assignments turned in before then. So I'm going to be here all Friday morning, turning in everything that you all have turned in by Thursday at midnight. Everything is due by Thursday at midnight, so that I can grade it all Friday morning.
And also, on the extra credit movie, it says Jurassic Park. Was it changed?
No, it was Jurassic Park.
Oh, I thought you were watching Greenland for some reason.
No. I mentioned Greenland was on there, but Jurassic Park won. Did you make a friend?
I told her to play rock, paper, scissors. She said no. She said I don't want to.
What did you ask her to do?
To play rock, paper, scissors.
Oh. Okay. What else?
Time limit on the exam?
500 minutes, like always. Same for your lab exam, by the way. Your lab exam is going to open as well. That's going to be fill in the blanks. Okay, those are just going to be fill in the blank questions.
How relevant are the extra credit questions are to the test?
The extra credit questions? The extra credit questions are relevant to our discussions on those subjects. The discussions on those subjects, things like gene therapy, dinosaur traits, things like that, are relevant to the exam.
Believe about it.
You can't what? So, in a roundabout way, some of the questions on the extra credit assignment might be connected to questions that could be on the exam. I'm not going to put anything on the exam about Jurassic Park. That wasn't a required material. It was an extra credit assignment. I'm only going to have things that were our required material to know on the exam. Hey, Liam. I love you. Hey, Liam. You're the bomb. You gonna say it? No? He'll just walk up to me randomly and say, "Hey, Dad, you're the bomb." Love how my little boy born in 2022 is picking up the mannerisms of his 90s dad. Everything is sick and everyone's the bomb. All right, what else? So module 1, remember, was kind of a review of 1403, where we talked about sedimentary rocks, environments, and how fossils are related to those. Module 2 was about how life changes, how evolution works, mutations, all of those sort of things, adaptations, what a positive and negative mutation are, the trends that we see in those through time. Yeah?
Are there any specific definitions we should know about?
Specific definitions, like word for word? Anything that I took the time to put the definition for on a slide is something that's good to know. I never require you to memorize anything, but it's always a good idea if I give you a definition to write it down. So things like phylogeny, clade, the principle of uniformitarianism, stuff like that that are recurring factors, those are good to know. Where did Isla go? She's under there. There she is.
He's in there.
Yeah, she's in there. Should you go find her? Do you want to go find her? Okay, go get her.
It's gone.
No, she's right there. Isla's gonna get you? Maybe. And then module 3 was this walkthrough of geologic time that we've been having, and a discussion about where certain organisms showed up in that timeline, and then where they went extinct from that timeline.
For lab 5, it's about the choosing a fossil and stuff.
Uh-huh.
Researching it.
Yep.
You want like a certain amount of words, or just covering them?
There's not a certain amount of words that I need on Lab 5 as long as you answer the questions. So what's the taxonomic classification? What period of time was this thing alive during? What was its life cycle like? All of this comes down to the research that you do on your own. Yeah.
And on that table for lab 5, what is exactly the asking?
Yeah, I'm just asking you to fill in, to like put an X in each box that that organism was alive. Yeah, so if it says dinosaur, you would put an X through Triassic, Jurassic, and Cretaceous.
Look.
What?
Look.
Oh, it's off.
Yeah.
Oh no.
It's not on.
You want me to turn it on?
Mhm.
Okay, I'll turn it on. Do you know what it's going to show us?
Look.
It's going to show us you.
It's not working.
Oh, it'll work. Hold on a second.
That's
Who's that?
this.
Yeah, who is that? Is that us? Yeah, it is us. And look, we're right here too. What else?
For the lab 5, do you have a specific
For Lab 5? So I've pointed you all in the direction of reliable resources for your discussion boards. If you're taking this class online, I've told you, or in person, I've pointed you towards things like nature.com or the Geological Society of America or things like that, geology.com, right? These are all reliable sources. If you want to go to Wikipedia for sake of convenience, that's fine, but do not use the information in Wikipedia. Go down to the bottom of the Wikipedia page. Let's say you choose Megalodon, okay? You Google Megalodon, you go to the Wikipedia page for Megalodon, go all the way to the bottom of the page to that part that says sources cited, and then click on one of those sources, because those are verified sources that the user who made the Wikipedia page used. And you can go there and be like, oh yeah, this is a legitimate source. Use that as your source, not the Wikipedia page. Fair enough?
Yes.
Hi. I'm not going to eat that. No.
So there's more than one graduation ceremony?
Yes, we have 3.
Okay.
We have 1 on Friday and 2 on Saturday. Although we are graduating 1,000 students this semester for the first time ever, and they're talking about maybe having a second Friday one next year. It's just going to be harder on us.
No. It's this. What?
What else?
Daddy, look at my hand.
Say what? I'm sorry.
So cold in here.
Oh, it's so cold in here?
Look at my
It doesn't feel
hand.
cold to me. You need to do some jumping jacks, brother. Get down and give me 10.
Daddy, look
That'll warm you up. I can't. I'm working. Hey, shh. I need to answer questions. What else do we got? Any questions about other labs or discussion boards?
Daddy, look at my hand.
You can turn anything and everything in still for full credit. If you have a 0 on anything, up until Thursday midnight, you can turn all that stuff in. Okay? Liam, you gotta hold it like this unless you want it to fall out. All right. Yes.
Daddy, look at my juice.
Sorry, say that again.
How much of our grade
Daddy, never
Is the exam?
Stop that.
Is the lab exam specifically 100 points? So 10% of the grade.
10%?
Yep. So exam 1, 10%. Exam 2, 10%. Exam lab exam, 10%. Final exam, 20%. Yep. So all exams in total are 50% of the grade, and everything else is the other 50%. That way, I have it equally distributed between exams and everything else, so that if you're good at taking exams, you just need to be okay at all the other stuff to pass the class. Or if you're bad at taking exams, you need to be great at everything else and okay at taking the exams to pass. So it's equally accessible to people regardless of which type of person you are. I always sucked at taking exams, but I excel at things like research, having meaningful discussions, lab work, anything that's hands-on like that. I did great at those, and as long as I was able to do okay in exams, I always passed my classes, and I want to kind of understand that there are people like me out there as well. What? Juice?
No.
Your juice is over there in that corner.
No.
No, you can't have my juice. That is special juice. It has stuff in it you can't drink. No, I'm sorry. No, I'm sorry. Mm-mm. Mm-mm. I put like adult multivitamins stuff in there. And it's got like stuff like natural energy stuff, so I don't want them to drink that. Their bodies can't handle it.
For the life cycles and lifetime, is it just like the time they grow to
Right, so an example of a life cycle for, say, something like a human. Gestation period, 9 months. Baby, until, 3 years. Toddler, so on and so forth. Something like a shark. Hey, I'm talking. I'm talking.
But I need that.
What do you need? You want that Play-Doh stuff?
Yeah.
You'll have to wait a minute. It's drying off. Something like a shark, you could talk about, okay, it's in an egg for X amount of time. And then it is a, what do you call shark babies? There's a name for it, but it's escaping me. For X amount of time. And then it turns into a juvenile. And then from there, when does it reach adulthood? How long is the average lifespan of a megalodon? Things like that. Generalizations about the life cycle.
Is it the box? The toy?
Are you playing I Spy?
Here's the pizza. I just
What do you say when you burp?
Excuse me.
Good job. What's up? Hello.
I decided this would be in better hands with you than just sitting.
Oh, really? Thank you. He drew Diablo. See? Yeah.
You did get the digital copy I sent you, right?
Yes. Yes. Thank you.
So yeah, there you go. You can have it.
All right.
I don't think I'll miss it.
I'll put it up with the other artwork my students give me. Appreciate it, man.
You get a lot of artwork.
Last one was probably a year and a half ago, so I don't have a whole lot, but I'll put it up on my wall.
Glad to add to your collection.
Yeah. Thank you, man. Hey, you graduating this weekend? I'll see you there.
See it.
Take care. Yeah.
For the fish fossil, you say the media is anywhere? Is that what you want to say?
Say that again.
For the fish fossil, you put media is that exactly what you want us to do?
Oh, on the thing? No, that's just the species. That's an example of something. Yes. You could look that one up if it's easier. Go for it. Do you know any other fish species off the top of your head? I would anticipate probably not. And saying just fish would probably be too general. So I gave you a species that you could look up. Yeah.
But this is from like any time period, right?
I mean, all those organisms represent on Lab 5 represent fossils throughout time, right? So they're cherry picked from different points in time.
I could have like an arm of fish or something.
Yeah, Dunkleosteus. You could pick Dunkleosteus if you wanted to. Yeah. No. Nope.
2, 3, 4, 5, 6, 7, 8, 9, 10.
What else y'all have for me in the last little bit we've got?
Other than some specific help on the lab,
Specific what?
help identifying something.
Like what?
It'd be better if I just showed you.
Sure, let's hold off on that then. Any exam relevant questions?
Use this.
I want to make sure everyone has an opportunity to feel good about the exam.
Okay.
This is your moment.
You hide and I will come.
You went for a walk, you feel a little warmer?
No pee.
Okay. Do you have any other exam relevant questions before I end this recording? All right. In that case, I am going to thank you all for taking my class. It's been fun. I've appreciated your interaction. I have appreciated your good humor with my bad humor often at times, being here in my class or for watching my lectures online. And I hope that what you've learned in my class has gone a long way towards improving your wonder towards our world and our universe that we're in. And I will end it there.